Good morning, students. Let us start the class. Yesterday I was discussing about the factors that are affecting the stability of the Q point in an amplifier circuit. So, the same thing I am putting here in this PDF notes. Beta increases with increase in temperature. VBE decreases by 2.5 millivolts per degree centigrade increase, and ICO doubles for every 10 degree centigrade increase. Yesterday I was mentioning why this ICO increases with increase in temperature. ICO is nothing but the reverse saturation current, and even the forward current is related to the reverse saturation current, as you have already studied in the diode current equation. And so typically the reverse saturation current doubles for every 10 degree centigrade rise in temperature, because every rise in temperature is going to increase the energy of the charge carriers, which are the electrons. So when current increases, naturally beta also increases with increase in temperature, because beta is again dependent on this particular reverse saturation current flow as well. In general, in philosophy, we say that yatha brahmande tatha pindande. Don't worry about why I am bringing philosophy into technology, because philosophy is always there with the technology. Without the philosophy, there is no technology as such. Why I told you this particular proverb is, just like the macrocosm is mysterious, the same way the microcosm is mysterious. Just like in the universe, we cannot count the number of stars. In the same way, in this body, we cannot count the number of cells. Just like in the macrocosm or in the Brahmanda, as the number of stellar bodies are infinite, the same way in the human body also, the number of cells are infinite. Now, why I am bringing that here in our discussion? The reason is, when we go deeper and deeper into the silicon surface, inside a transistor, we have P-type and N-type semiconductors, and we really don't have a count of the number of silicon atoms or the number of dopant atoms as well. So naturally, it is a quantum world there. The quantum world means there are some mysterious laws which are governing the quantum world, where in the normal visible nature or in the normal visible technology, the laws are visible to us. The laws we can manipulate to some extent, and we can utilize these laws for our benefits. But in the quantum world, or in the subatomic world, the world which is below the atoms, there it is only charge carriers. Few centuries before, people were thinking that electrons are the smallest particles. Later on, they have found out so many other particles which are smaller than the electrons. You might have heard about this Higgs boson particle, which was already called as God particle. Why they called it as God particle? Because they thought that it may be the smallest particle as of now. Maybe after about 10 years, again they may invent one more smaller particle than that. As of now, they have called it as a God particle, which means there are particles which are smaller than electrons. They are called quarks. There are particles which are smaller than quarks, and they go to a particular theory called string theory. So in this way, why I am telling all these minute details is, in the quantum world, all the things are not happening as per our will and wish, and as such, the nature is non-linear and the materials also are non-linear. So in the quantum world, there are some mysterious laws which are taking place. We can say they are God's laws only. Whether you believe in God or you don't believe in God, it does not matter much, but you should believe that the universe is planned, and the life is planned, and the nature is planned. When nature is planned, when life is planned, when universe is planned, there must be a much bigger power that is planning and handling the complete universe. So if you understand that way, that is enough. That itself is a great knowledge. So let me come back to the technicalities of our biasing circuits. Why I brought out all those philosophical points here is, when ICO doubles, when the reverse saturation current doubles, even beta increases with increase in temperature. Otherwise, you may think that why should beta increase? Because when IB is changing, IC is also proportional to changing. Beta should not be changing. That may be your way of thinking. But as I told you, in the quantum world, the laws can be altered in many ways. Ultimately, life is always dependent on an ambient temperature, which means in an ambient temperature of, let us say, 25 degrees centigrade till 40 degrees centigrade, we are living here. Above that particular temperature, we may not be able to live. Below a particular temperature also, we may not be able to live. That means everything is governed by temperature in nature. So if temperature changes, we cannot exactly predict in what way the nature is going to change. So that is how, when reverse saturation current doubles for every 10 degrees centigrade increase in temperature, beta also increases with increase in temperature. And then, as I told you yesterday, VBE reduces when the temperature increases. Why? The PN junction is basically a non-linear material. It is a combination of two dissimilar materials. P is different, N is different. Whenever we combine two dissimilar materials, its behavior or its characteristics cannot be well defined by the mathematical laws. That is when we say diodes and transistors are non-linear when compared to resistors, capacitors and inductors, which are linear. Because resistor follows Ohm's law. Even capacitor and inductor, they also can follow Ohm's law. For example, XC is 1 over 2 pi FC. XL is 2 pi FL. Which we can say that to some extent reactance is following Ohm's law, because reactance is nothing but the AC counterpart of resistance. So that way resistance, capacitance and inductance are classified as passive devices because we can predict their behavior for a given DC or AC condition. But we cannot predict the behavior of diode and transistor so easily because they are non-linear devices. So wherever there is non-linearity, whenever this current is increasing, resistance is reducing. Whenever the resistance is reducing, the voltage drop across the PN junction is reducing. So, to some extent they have quantified the change in these values, and they have found out that VB decreases by 2.5 millivolts per degree centigrade increase, and ICO doubles for every 10 degree centigrade increase. Now, if this is the case, how our circuit remains stable? Naturally, the circuit will not remain stable. Only the voltage divider bias circuit will remain stable if at all that condition of beta RE must be greater than or equal to 10 R2. If that condition is satisfied, then we can say that voltage divider bias is stable compared to all other biasing circuits. Let me continue. If you have any questions in between, you can always put it in the chat box, or you can unmute yourself and you can ask me. Let me continue now. Now, due to these reasons, the value of IC changes, the collector current changes, and hence the Q point gets shifted. When the collector current changes, naturally ICRC changes. If ICRC changes, even VCE also changes. Therefore, the stability factor of a biasing circuit can be defined in three ways. Now, as there are these three things which are subjected to change with the temperature, we can say that stability with respect to ICO, that we call it as S of ICO. We call it as delta IC by delta ICO. That means the rate of change of the collector current with respect to the rate of change in the reverse saturation current. Similarly, the stability factor with respect to VBE, that is S of VBE, equals delta IC by delta VBE, which means the rate of change of collector current with respect to the rate of change in VBE. Lastly, S of beta or stability factor with respect to beta is delta IC by delta beta. That means rate of change of collector current with respect to the rate of change in beta. Now these three are three different stability factors. In fact, there are bigger equations for these three stability factors for all of these three biasing circuits. But we are not dealing with all those big equations because it is not of much use for us. Otherwise also, in the prevalent electronics industry, BJT is used less and MOSFET is used more. But as MOSFET is slightly difficult to understand when compared to BJT, we are discussing BJT as well as MOSFET in our syllabus. Otherwise, BJT is less used in the industry. You will know about the reasons why BJT is less used and MOSFET is more used in the coming classes in this course also. And you will have one more course in 5th semester called CMOS VLSI design. There you are going to study more about the MOSFET related designs only. Okay. So there is no need to go into the equations which are there for each of these stability factors. This primary equation is enough. Otherwise, these stability factors are expressed in terms of the transistor characteristics and in terms of the biasing elements also, in terms of the resistors which are used for biasing. But we are not going into those details. Those who are curious to know the equations, you can always go through the textbook, it is mentioned there. But we have not kept it in the curriculum because unnecessarily we should not keep on working out bigger equations which have no value as such in the industry now. So these are the three stability factors, means for any given biasing circuit or for any given amplifier circuit using BJT, we can define stability in terms of these three factors. Why they are separately defined? The reason is change in beta is different, change in VBE is different, and change in ICO is different. So we cannot standardize all these three and we cannot say a single stability factor. That means we should always mention that the circuit stability factor with respect to ICO is this much, with respect to VBE is this much, and with respect to beta is this much. Now, what will be the ideal stability factor here? The ideal stability factor will be 0. Why? At the numerator you have this delta IC. At the denominator you have the other factors like ICO or VBE or beta. Which means if collector current does not change at all with respect to any of these three things, then S of ICO is 0, S of VBE is 0, S of beta is 0. Which means an ideal circuit will have a stability factor 0. So, if the value of S of ICO is much larger, then it means that the circuit is much unstable. Please understand that. Because we are defining the stability factor with respect to the rate of change in collector current. So, if the collector current does not change at all, then the stability factor is 0. And if the stability factor is 0, that means the circuit is ideal, circuit is completely stable. So, if at all a biasing circuit is having a stability factor of 10, and if at all another biasing circuit is having a stability factor of 20 with respect to ICO, then we should come to a conclusion that the circuit which is having S of ICO equals to 10 is more stable than the circuit which is having S of ICO as 20. Which means that the Q point of the circuit which is having S of ICO 10 will not vary much when compared to the Q point of the other circuit which is having the stability factor of 20. So the point here is lesser the value of the stability factor, better is the circuit. Larger the value of the stability factor, worse is the circuit. That is the conclusion, and the conclusion is based on these definitions only. Let me continue. Lower the stability factor, better is the circuit. That's what I told till now. As it is less sensitive to temperature. VDB has the least stability factor and base bias has the highest stability factor. This I have been telling you earlier also that in base bias, as soon as the base current changes, collector current changes, and there is no way in which we counteract for the change in collector current. This I had discussed at length earlier. So naturally, voltage divider bias has the least stability factor and the base bias has the highest stability factor. The stability factors of all other biasing circuits are lying in between. Means we have discussed three circuits there. The stability factor of the self bias is lying in between. There are many other biasing circuits that are available in BJT, but we have purposefully not put them in curriculum at all because they are not of much practical importance nowadays. So we have discussed only three biasing circuits primarily. So just look at this diagram now. X-axis is VCE, Y-axis is IC, and this is the load line. In the load line, Q point has to be ideally at the middle of the load line. So ideally, the Q point should have a coordinate of VCC by 2 and IC sat by 2. Now you can see in this diagram, the base bias Q point can shift towards saturation or towards cutoff in a large manner, whereas that of VDB is changing much lesser. So the Q point of the self bias can be somewhere in between. I have not mentioned it here, but I have mentioned already to you that all other biasing circuits will have the stability factor which is in between VDB and base bias. So base bias is the completely unstable or highly unstable circuitry, whereas VDB is the most stable circuitry. That is what this particular picture indicates. Now let us see a method called bias compensation. There are some methods. These methods are discussed in Millman and Hucky's textbook. There were some good points there, so we thought let us keep them in the syllabus so that there will be more clarity in understanding about how circuit can be made better. So in order to overcome the effects of VBE and ICO on the collector current, the circuits can be compensated, which means the circuits can be provided with some other additional component such that the circuit will become more stable. That is called bias compensation. So let me explain you this particular circuitry which is called diode compensation for VBE. Now just look at the circuitry. Here we have this particular base bias itself or self bias itself. Or even this RB can be replaced with that R1 plus R1 parallel with R2. Now this is a general biasing circuitry where we have the biasing resistance at the base and we have at the collector as well as at the emitter. Now just look at the circuitry. You don't have to worry much about the value of V or this value of VCC. Slightly the notation is different here, because this circuit is taken from the other textbook, the third textbook of Millman and Hucky's. He has used the notation of V here for the biasing supply at the base, and he has used one more power supply called VDD. This especially is mentioned as VDD because it is used for bias in this particular diode. Now look at the circuit. RB, RC, RE are common with all our earlier circuitry. The only difference here is this diode which has got a voltage across that is notified here as V0, and then we have this RD and then we have this VDD. Now this diode is purposefully kept in this direction. Diode is kept in the reverse direction when compared to VBE. You have to visualize one diode from base to emitter, that itself is VBE. Now there is another diode which is in the reverse direction, that is this V0. Now you may think that this diode may not conduct because it is connected in the reverse direction, but you can look at the power supply given to the diode. VDD is given to the diode along with one series resistance RD. VDD is purposefully given such that the diode remains forward biased. That means when the circuit is working, even the diode is working because diode is working in forward bias condition. Okay. because its cathode is connected to negative of VDD, anode is connected to positive of VDD. So this diode is forward biased with respect to VDD. And why RD is given? Because we know that even though we generally take the drop across diode as 0.7, actually it is not so. So we give a supply voltage of, let us say, around 1 volt or 2 volt here, that is VDD. Remaining voltage will be across RD, so that whatever is the forward bias voltage drop, that will be across the diode. That is the idea here. Now what happens in the circuit is, we have an additional diode, we have an additional resistor, we have an additional power supply. This is called as a compensation circuit. Now what happens here is, if temperature changes, VBE changes. Now if temperature changes in the transistor, base to emitter junction potential changes. But when temperature changes, that drop across the diode also changes. You can see this PN diode at the base to emitter, and there is another PN diode from the ground to the emitter side, which means we have connected two diodes back to back. There is already one base to emitter diode, we have connected another diode. So what actually happens here is, if this base to emitter's VBE changes, accordingly in the other direction, the drop across the diode also changes. That way they compensate each other. I hope you got this point now. The diode at base to emitter and the diode which is connected below, they are in opposite direction. But current keeps flowing because the diode at the bottom is forward biased by a separate power supply. So transistor will keep working, and even the biasing circuit will keep working, amplifier will keep working, because this V0 is forward biased. But when VBE changes, V0 also changes, and they are in opposite direction. You can see that. Let us say VBE is 0.7 here, this V0 is 0.7 here, diode is conducting. Let us say now, because of the temperature increase, let us say VBE becomes 0.8, here also V0 becomes 0.8. But they are in the opposite direction, so somehow the voltage at the base remains constant. Just imagine, let me give you an example. Let us say this voltage at the base is around 2 volts. If the voltage at the base is around 2 volts, let us say VBE is 0.7 and here it is minus 0.7. Across the, if you apply KVL here, across the other diode V0, it is minus 0.7, because they are in the opposite direction. Just remember the thing I had told you yesterday. Whenever we move from positive to negative, we have a convention. Whenever we move from negative to positive, we have another convention. Shortly, I will show you those KVL equations also, which is there in these notes now. So let us say at the base it is 2 volts, and let us say at the base to emitter it is 0.7, and at the diode you see it minus 0.7. Now the remaining voltage is across this RE. Now due to the increase in temperature, let us say the base to emitter voltage increases to 0.8. Now in the reverse direction also, the diode drop increases to 0.8. So the difference remains the same. Earlier this was one direction 0.7, this was other direction 0.7. Now this is one direction 0.8, other direction 0.8. That way they are balancing each other. So the drop across RE remains the same, and the voltage at the base also remains the same. That means Q point is not affected at all. That way the circuit is working in a stable manner. So let me come to the application of KVL now for this given circuitry. Whatever I have told you, again I have mentioned it here. VDD is used to keep the diode in forward bias. When the diode is of the same material as that of the transistor, then both VBE and V0 will have the same effect when temperature increases. This is very important. Diode as well as the transistor must be of the same material. Means if this is silicon, this also has to be silicon only. And the doping of this silicon and this silicon must be same. Only then VB and V0 will be equal. Now applying KVL at the input side, At the base we have a supply voltage called V minus IE by beta into RB. That IE by beta is nothing but IB. IE by beta into RB minus VBE minus IERE plus V0 equals 0. You can see V0 we have written in this as plus symbol, because in the circuit when we go from negative to positive we use a conventional sign as plus. When we go from positive to negative, that is a loss there in the circuitry or a voltage drop there in the circuitry. For that we use the symbol minus, you use the sign minus. So accordingly, if you apply a KVL here, let me annotate this input loop. When we apply a KVL here like this, now we are going from negative to positive. So V and minus IBRB minus VBE minus IERE plus V0, because we are going again from negative to positive, plus V0 equals 0. That is how we apply KVL. Now for this IB, we can always write IE by beta for our clarity. Now we can simplify this equation. V minus VBE plus V0 is IE into RE plus RB by beta. Or we can find out IE equals V minus VBE plus V0 divided by RE plus RB by beta. Now look at this equation. In this equation, minus VBE plus V0 are there. Which means, if there is a change in VBE, there is a change in VBE, but the signs are minus and plus, so those changes get cancelled out here. So the IE is basically proportional to V divided by RE plus RB by beta. So this expression for the emitter current indicates that if VBE changes, V0 also changes in the other direction, so IE remains constant. If IE remains constant, Q point remains constant. So this is called as bias compensation for VBE. As the change in VBE and that in V0 are same, both get cancelled out. As I had already told you, VBE is having minus sign, whereas V0 is having plus sign. Both are equal and opposite, so the changes get cancelled out. Now let us see one more circuit, which is the diode compensation for ICO. We had seen a circuit where the circuit was compensated for the changes that are occurring in VBE. Now in this particular circuit, if there is a change occurring ICO, even that is compensated. Let us see how is it compensated now. Here a diode is connected in the reverse bias. Now the diode is working actually in the reverse bias only, because there is no other power supply for the diode. It is purposefully kept in the reverse bias. Why? Because what is ICO? ICO is nothing but reverse saturation current. Now we want to compensate for the change that is occurring in the reverse saturation current. So this diode is connected purposefully in the reverse direction. Now what happens here is, there is ICO in this direction and there is ICO through the transistor's junction as well. As the ICO is flowing in the reverse direction when compared to the main current, we have to visualize one more diode here. Plus to minus is that base to emitter diode, whereas in that base to emitter diode, the reverse current is flowing in the other direction, right? So if temperature increases, then if at all there is a change in this ICO which is flowing through the base to emitter junction, there is another diode connected in the other direction, and that same change will occur here also in the other diode. Just like there we had one VBE compensation where we purposefully connected a diode in a forward bias. Here we are connecting a diode at the base in the reverse bias, and whenever there is a change in the reverse saturation current in the base to emitter junction, the same way, because this is also made up of the same material. The diode as well as the transistor both have to be made up of the same material. Now the same change will occur in the diode also in the reverse direction. That is how even the reverse saturation current gets compensated. So the same thing is explained here. As the diode is reverse biased by an amount of VBE, The current through the diode is the reverse saturation current because it is directly across base to emitter. The current through the diode is the reverse saturation current. In general, IC equals beta IB plus 1 plus beta into ICO. Generally, we ignore this 1 plus beta into ICO in our normal calculations. That is because this ICO is always in nanoamperes, whereas IB is in microamperes. There is nearly 1,000 times difference between the reverse saturation current and the base current. So for all our normal calculations, we basically ignore the second term, that is 1 plus beta into ICO, that we generally ignore. But whenever we have to compensate for ICO, now we cannot ignore. So we write the accurate expression for collector current, that is beta IB plus 1 plus beta into ICO. From the circuit now, IB is nothing but I minus I naught. You can see base current is nothing but total current I is coming from the power supply minus the reverse saturation current I naught. I naught is nothing but ICO itself because this diode is reverse biased. So from the circuit it is IB equals I minus I naught. Now this can be substituted in the upper equation. So IC equals beta into I minus I naught plus 1 plus beta into ICO, or IC equals beta into I minus beta into I naught plus beta into ICO. That particular 1 can be ignored here as beta is much larger than 1. This digit 1 can be ignored. So now we have an expression where IC equals beta into I minus beta into I naught plus beta into ICO. Now look at this expression. We have beta into I, this minus beta I naught and plus beta ICO. There is a opposite sign here. But we know that I naught and ICO both are same. So a change in ICO is going to cause a change in I naught as well. So the total change gets cancelled out. So that is how this particular circuitry is compensating for the change in ICO. As the change in ICO and that in I naught are same, IC remains essentially constant. Okay, this is how we are discussing two circuits. One is for VBE compensation and one is for ICO compensation. These are the techniques which they had developed many decades before so as to keep the Q point stable. But now anyhow, these are all not under usage as such because gradually MOSFET has taken over BJT. BJT is larger in size, MOSFET is smaller in size, and as such we need electronic products which have to be lightweight, which have to be smaller sized. So that is how everywhere the electronic products got designed primarily by MOSFET and not by BJT. So that is how all these circuits are of not much of application now. But as students, you should understand the way in which the scientists in the earlier decades worked hard to keep the circuit stable. That is the idea here. In fact, in technology, so many solutions are coming out only through these ingenious ideas of the scientists and engineers. Let me come to the last part of this particular DC analysis. Later on, we are going to gradually go into AC analysis. So, the last part of this DC analysis is thermistor and sensistor compensation. In the last class, one student asked me that whenever temperature increases, the resistance also increases. I am going to tell you today, it is not the case. There is something called thermistor, there is something called sensistor, and there is something called as positive temperature coefficient, and there is something called as negative temperature coefficient. So you can see in the screen now, you can see these two circuits. There is something called thermistor compensation and there is called sensistor compensation. You have something called RT here, that is called as a thermistor, and you have something called as RS here, that is called as sensistor. Now, the thermistor has a negative temperature coefficient. Look at the circuitry. This thermistor RT has a negative temperature coefficient. So what happens here is increase in temperature causes reduction in the resistance, causing increase in IE. I'll come back to the circuit now. If this particular thermistor has got a negative temperature coefficient, means increase in the temperature is going to reduce the resistance in this case now. Now when it is going to reduce the resistance, what happens here is we have a path of current here. We have one path of current in this direction and we have one more path of current in this direction. One current is coming from RC to RE, one more current is coming from RT to RE. So the net current across RE will not be actually IE, it will be more than IE. Okay. Now when temperature increases, RT reduces. If RT reduces, current across this particular path increases. If current across this particular path increases, now the drop across RE increases. When the drop across RE increases, it is going to reverse bias the base to emitter junction. Just recall why we put this RE in the first place in the self-bias circuitry. I had explained that in detail at that time. So just recall all those basics. If at all the current across RE increases, there will be a voltage drop across this RE and that is going to reverse bias the base to emitter junction. So that is how increase in temperature is going to reduce the value of RT. Reduction in the value of RT is going to increase the voltage drop across RE. The voltage drop that is increased across RE is going to bring the transistor back into active region. If at all current increases, then it will gradually move towards saturation, right? But if it moves towards saturation, we have a thermistor here. Now the thermistor is going to have a lesser resistance. So the current across RE increases. If the current across RE increases, slightly the base to emitter junction will be reverse biased and the transistor will come back to active region. This is called thermistor compensation. On the other hand, we have something called sensistor compensation. Now thermistor is having a negative temperature coefficient, whereas sensistor is having a positive temperature coefficient, which means that when temperature increases, the resistance increases. Now both these circuits are having the same functionality. Only thing is connections are different. The connection of thermistor has to be like this here, so that when temperature increases, it will cause the increase in the current at the RE. But what happens in this case, in the other case of when we connect the sensistor here? Now you can see here, we have a path of one sensistor, we have one more path of this main path, where from the emitter current is coming down. So if at all temperature increases, what happens is the voltage drop across RS, what is going to happen? It is going to increase. Why? If temperature increases, this value of RS is going to increase. When the value of RS is going to increase, it is going to cause an increased drop across this. Now the increased drop across this RE, because RE and RS are in parallel. Now when RE and RS are in parallel, when the resistance RS increases, the effective resistance also increases. Why? RE is in parallel with RS. So when there are two parallel resistors, if one resistance increases, the net effect of the parallel resistance also increases. So when it increases, voltage drop at the emitter increases. When the voltage drop at the emitter increases, again the same effect happens. Means across base to emitter, there is a slight reverse biasing and the transistor will come back to active region. The transistor will never be able to go into saturation region. That is how using thermistor and sensistor, the circuits can be compensated. So whatever I have told you, I have put it in the notes again. The thermistor RT has a negative temperature coefficient. This increase in temperature causes reduction in RT. RT is thermistor, causing increase in IE. which will reverse bias the BE junction, thus preventing the increase in IC. Okay, preventing the increase in IC. Now, the sensistor RS has a positive temperature coefficient, thus increase in temperature causes increase in RS, causing reduction in IE and IC. Alternatively, thermistor can be connected in parallel with R2. See, the same RT can be connected in parallel with R2 here. That is another way of achieving the same purpose. What happens here is, if this thermistor, instead of connecting across emitter and the power supply, if it is connected across base and ground, what happens is, when temperature increases, this RT reduces. When this RT reduces, current at the base reduces. Why? When this RT reduces, the voltage at the base reduces. When the voltage at the base reduces, current at the base reduces. When current at the base reduces, transistor comes back to active region. So, this RT can be connected in parallel with R2. In the same way, this RS can be connected in parallel with R1. Okay. As I told you earlier, for a single problem, there can be multiple solutions. Now, these are all the multiple solutions. You are already seeing two solutions. There can be another two solutions like RT connected in parallel with R2 or RS connected in parallel with R1. If RS is connected in parallel with R1, what happens? When temperature increases, RS increases. RS is in parallel with R1. So, when temperature increases, the effective resistance from the power supply to the base, that increases. If it increases at the base, the voltage reduces because the base current reduces. When the base current reduces, naturally the transistor comes back to active region. That is how there are many ways of keeping this circuitry compensated so that the Q point remains stable. So, alternatively, thermistor can be connected in parallel with R2, which will cause reduction in IB. Similarly, the sensistor can be connected in parallel with R1, which will again cause reduction in IB. With this, I am coming to the end of the DC analysis. In the next class, we will start with AC analysis, and attendance link I will be posting in the Google class. Please mark your attendance. See you in the next class.